is a professor of automatic control at the Department of Electrical and Electronic Engineering of University of Cagliari, Italy. He has also had academic and visiting position in several institutions worldwide, including Xi'an University, China, and Aix-Marseille University, France. His research interests include discrete event system, hybrid system, network control system, pattern and failure diagnosis. He is currently the editor-in-chief of IFAC journal Nonlinear Analysis, Hybrid System, and a senior editor of the IEEE Transaction on Automatic Control. He is serving as a vice president for conference activities of the IEEE Control System Society. He is a fellow of both IEEE and IFAC for his contribution to discrete event and hybrid system. And he received in 2017 the People's Republic of China Fellowship Award. Today, he is going to give us a talk on stability and consensus in non-multi-agent system via nonlinear parallel forbearance theory. Thanks, Professor Deer. The floor is yours.
Thank you very much, Lilian. First of all, let me say that I'm very happy to be virtually in Brazil and to be giving this talk. And I would like to thank the organizers of the 2021 Simposio Brasileiro de Automação Inteligente. I don't know what I'm saying, for inviting me.
It's so
good. Okay, I didn't try it before. So yes, as you said, the topic is about stability and consensus of multi-agent systems. Let me say that this is not a topic in which I am the main author. Here, the main author is Diego De Plano, who was my PhD, the first author, who was a PhD student, and he just defended his thesis earlier this year. And also Mauro Franceschelli, my colleague from the University of Cagliari, which co-supervised the thesis of Diego. So let me give you a very small outline of my presentation. Of course, some motivation. Why are we studying this problem? Then I will do a part where I will review the problem of consensus via Perron-Frobenius theory in the linear case, that is the case that has been mostly studied. Then I will show how it is possible to extend the analysis of nonlinear, to extend to nonlinear multi-agent systems, the study of consensus. And I will give some application, and I will discuss some ongoing research directions. Okay, so first of all, what is an agent? Well, agents are computational systems that inhabit some complex dynamic environment. They sense and act autonomously in this environment. And so they realize a set of goals of tasks for which they have been designed. Of course, this definition is very abstract because it wants to, to take into account a lot of different possibilities. But when we want to specify and look at agents, what are these computational systems that act autonomously? For instance, a self-driving car. It's an application that's very important right now, but also human opinions, a player that plays an arbitrary game, a computational unit, and so on. So if an agent is this object, it's easy to understand that a multi-agent system is a system that contains different agents. Agents are coupled through a network. They work together to find answers to problems that are beyond the individual capabilities or knowledge of each agent. So in fact, in all those 4 examples that I mentioned before, if we have a network of autonomous vehicles, then we can consider the problem of controlling an automated highway. If we have a lot of players, then we can develop a game theory to understand how they interact and what will happen by their interaction and so on. Another thing that I didn't put in the slides, but I want to mention is that when we consider multi-agent systems, there is an emerging behavior. What I want to say, well, let's suppose we consider an ant and an anthill, a colony of ants. Well, the ant is stupid, is doing very few things, but the anthill, the ant colony, is an intelligent system. It has an emerging behavior which is very, very complex. Now, the first thing I want to point out is that I'm talking, of course, and I'm seeing the things from a control system point of view, but multi-agent systems are a paradigm that spans a lot of different domains. And this sometimes can create confusion because you hear the word multi-agent system, I hear the word multi-agent system, and I understand it from my point of view. Instead, we have to be careful. Other communities may be meaning something slightly different. So in the control community, agents are dynamical systems, and the graph represents the pattern in which they are coupled, okay? But if we look at the computer science community, their agents are software agents. So they are self-organized, they try to solve a problem with learning, artificial intelligence, and the graph that describe how they are interconnected denotes how they exchange information. Well, and there are many, many other areas. I don't want to go over them because I know that I will be a bit, I will run late if I do that. But multi-agent systems are useful, are be considered by the community of energy systems, operation research, distributed optimization, robotics, and so on. Okay, now let's go back to control systems. So let's look at an agent as a dynamical system. Well, in this case, as with all dynamical systems, the agent will be modeled using 3 main signals. That is the state of the agent, I, the input of the agent, I, and the outputs of the agent, I. And this representation can be either in continuous time or in discrete time. In continuous time, we have this standard state variable description. The derivative of the state of agent I is a function of the state of agent I and of the input of agent I. And the output is a function of the state. Well, in discrete time is almost the same thing, but instead of having a differential equation, we have a difference equation. So we have that the agent I will update its state at times k plus 1 based on the info of its previous state and of its previous input. Now, let's simplify a bit things. First of all, we are considering only discrete time models. At least this is what I will do here. I assume that the state of the agent is just, is just a real number. So it's not a vector, but it's a real number. The output of the agent is nothing else than its own state value. And the input of the agent, well, the input of the agent is given by the states, the values of the states of the agents in this set Ni. So Ni is the neighborhood of agent I. That is the set of agents who directly influence agent I. So we can go to this it's basically the same thing I said before, but I could say that a single agent in discrete time can be modeled by this equation. So the agent I will update its states as a function of its own state and of the state of its neighbors. Now, if we consider a multi-agent system that is composed by n agents, well, then we can consider an overall state of the system. This state, of course, is given by as many components as there are agents, in this case, n, and we can give this representation. Now, this representation It's quite intuitive, but I want to stress here two things. If I look at the first part, so I ignore this part, and I see that xk plus 1 is equal to f1, f2, fn, I can see that the way that the state of the overall system is updated depends, of course, on the current state of the system, but also on the state of the interconnections, because here I have all the neighborhoods of the agents. However, if I look at it as xk plus 1 as a function, I don't need to know how that function is related to the structure. So then it's a standard xk plus 1 equal f of xk, okay? Which is the definition of a standard autonomous system. So these two ways of looking at a multi-agent system, focusing on its overall behavior, and so leveraging on the control theory. We have a lot of results for this class of systems. Or looking at the interconnection, we should try to exploit these two different interpretations, let's say. Okay, now, what is the problem? A lot of problems can be addressed in this context, but the problem I will be discussing is just one. It's the so-called consensus problem. So let's suppose I have a set of n agents from 1 to n. Each agent has state xi, and this type of dynamics. So the consensus problem consists in designing a set of local interaction rules, those functions that tell how each agent updates its state, so that all the agents converge to the same constant state. In other words, reaching a consensus problem means making sure that for any initial condition x0 of the overall system, there exists a real number, alpha, which in general depends from x0, such that the limit of the overall state is a vector where all components are identical. So I can write it as alpha x0 times a vector of ones. Okay, now, is the consensus problem an interesting problem? Well, it's very interesting. And let me just give some examples of things, of dynamics that, or problems that can be modeled as a consensus problem. Suppose I have in the fields a network of chip sensors that are determining the correct value of a measure. Humidity, temperature, this is very useful if we want to control, I don't know, what's happening in a forest. So the idea would be that reaching a consensus could be computing the correct value of the measure. And how? Maybe by averaging, or maybe we want to compute the median, which is a more robust statistics, or maybe the max or the mean, which is even easier. Another problem that is a consensus problem. We have a flock of mobile robots, and they must agree on a rendezvous point. How is this rendezvous point chosen? Depends. Possibly a good choice would be to choose the barycenter, because it's probably the point that can be reached more easily from all the robots. Another problem that doesn't seems like a mathematical problem. A population who wants to choose a leader. So you will be choosing next year, I think, the president of Brazil. And so that is a problem of consensus. Even Italy is choosing the president next year, but in Italy, the president is elected by the parliament. So it will be a consensus restricted to a much smaller set. And again, there are many other problems that can be measured, can be modeled as consensus problems, but I don't want to discuss them at the moment. But if you look at the slides later, you will find them here. Okay, now, what about some literature on consensus algorithms? Well, it's funny because although the problem of consensus started to be addressed in the extensively in the control system literature in the new millennium after 2000, there was some work, like this work of Tsitsiklis in his PhD thesis, actually, in 1984, who introduced a lot of interesting concepts. Problems in decentralized decision-making and the computation. So it was, I think, ahead of its time. That thesis was much advanced with respect to the current problems considered by our community. Another interesting paper is this one, 10 years later, that was considering self-driven particles, and even there was a notion of consensus reaching some common point. So what is instead, I mean, the works instead that started, let's say, well, consensus became quite well known in the control community, starting the work of starting with SBAI and also Olfati Saber, so about 2003, 2004. And then there have been a lot of other interesting works. I cannot review all the literature. I wouldn't even be able to. I just put here some works that are considered very, very important in the community. However, let me say, when we look at the consensus for multi-agent systems, at least in large areas, what has the research been doing? Well, the main work, especially at the beginning, have been that of considering multi-agent systems with linear interaction rules. And here, since the first work, SBAI, as I was saying, it was clear that Perron-Frobenius theory, a theory of positive non-negative matrices, plays a fundamental role. So here I suggest, if you are interested in this, to read the book by Francesco Bullo. This is actually a book that you can download online and contains a lot of interesting material on this topic. However, also discontinuous interaction rules have been considered. In this case, we need a different technique for the analysis of these type of systems. And the proper approach, I mean, what has been used is the so-called non-smooth analysis. For this, I can suggest an interesting survey by Jorge Cortés, Discontinuous Dynamical Systems, in the Control System magazines. But there have been also other nonlinear interaction rules that have been considered, not necessarily discontinuous. Well, they have been addressed, for instance, using the Lyapunov function, again, non-smooth analysis. And here there is a very interesting paper which has, which has been cited a lot. So the first question is, but why do we have to consider nonlinear systems? Because many of the systems where we do consensus, we decide the function f. So we choose the function f. So we could say, okay, we just have to choose a function f, the local interaction rule that is linear. Well, but sometimes it's not, it's not always possible to do that. First of all, there may be physical systems that are interconnected, for which consensus problem is important. Consider a flock of birds, for instance. And maybe we need to study nonlinear interaction laws. But even if we can design the interaction, the multi-agent system, so we can choose the local interaction rule, there are some advantages in choosing nonlinear interaction rules. For instance, we can use them to get finite time convergence, or they are also much better at disturbance rejection, and so on, okay? So it's not just an abstract problem considering nonlinear interaction rules. So now, as I said, consensus for nonlinear system has already been studied in the literature. However, the solution is usually on a case-by-case basis, or sometimes for special classes. Sometimes the special classes are also restricted. So the idea is, well, since there is a Perron-Frobenius theory that is so successful when we consider linear interaction rules, what about nonlinear Perron-Frobenius theory? In fact, I didn't know there was even a nonlinear Perron-Frobenius theory, but in 2017, I was visiting a colleague in Paris, and he's a mathematician, and he had this very nice book about nonlinear Perron-Frobenius theory. And so there came the idea of why don't we try to see if there is something that we could use. And this is a bit, the story I will be telling you is the story that, originates from reading that book. Okay, now, before I present how Perron-Frobenius theory, nonlinear theory, can be used, I need to present how the consensus of multi-agent system is done in the linear case with the linear Perron-Frobenius theory, okay? So let me go back to the, maybe I've presented this before, but a multi-agent system that consists of an agent that follow the local interaction rule, where each agent is driven by the value of its neighboring agents, can also be written, as I said, by considering that the state of agent I depends from the state of all agents through a matrix A. And in this matrix A, there will be some element 0 if agent J does not belong to its neighborhood, okay? So for instance, consider this case in which X1, X2, and X3 are the states of the three agents. Agent 1 is updating its state, looking at its own state and the state of agent 2, and so on. So you see, this can be represented by this matrix where there are 0 to denote that there are some agents that are not influencing other agents. Now, what's the solution of this equation here? Well, everybody knows it. Starting from an initial condition, x0, the solution of this linear equation is the following. X of k is equal to a to the k times x0 for all values of k greater than 0. But now we are not here considering so far the network, because we said agents are connected to a network. How can we introduce a network? Well, we can associate a graph to the matrix A. And so we can consider, represent the interaction of the agents by a graph where the node, the set of nodes V is equal to the set of agents. The interactions is described by this set of edges, and each edge ij corresponds to an element iej of the matrix big A that is different than 0. Actually, here I put greater than 0, it's a mistake. I want to say different than 0. And also I could say that the neighbor of agent I are those agents j such that aij is again different than 0. So in this case, where we have this rule, this evolution and this matrix, I can consider the graph of this multi-agent system. So since the matrix A is order 3, there will be 3 nodes. And since agent 1 is influenced by 1 and by 3, from the node 1, there will be an arc going to 1 and an arc going to 2. Since agent 3 is only influenced by himself, from 3, there will be an arc going to 3. Okay, so this is the graph that describes how these agents are interconnected. Okay, now I have to say something about the interconnection of these agents because it's very important to understand how Perron-Frobenius theory works. So let's suppose I have a directed graph like the one I used before to describe the agents. So I can say that a directed graph is strongly connected if there exists a direct path from any node to any other node. I start from a node, I move along the arcs in the direction of the arc, and I can go everywhere. A sync component of a directed graph is a maximal subgraph, which is strongly connected. Inside this component, I can go everywhere, and it has no outgoing edges. Once I go there, I cannot get out of this component. And finally, we say that a sync component is aperiodic if the greatest common divisor of the length of all its cycles is equal to 1. Let me give you some example. Here I have a graph with 4 nodes, and I can partition it in 2 components. One component contains only node 1, and the other component contains node 2, 3, and 4. I can go everywhere. If I start from 2, I can go to 3, to 4, and so on. Now, how about the component? So this component, I label it with S because it's a sink component. The other component is not a sink because there are going out. So it's a transient component. So now this component, there are three elementary cycles. One cycle passing through 2, 3, and 4 of length 3. There is another cycle between 3 and 4 of length 2. So the greatest common divisor of 3 and 2 is 1. So it means that this component is aperiodic, okay? Let's look instead at this other graph. Well, this graph has the two components of the previous graph, but it has an additional component, which is this. Also, this component is a sink component because there are no arcs getting out of it. But if I look at the cycles here, there is only one elementary cycle of length 2. So the greatest common divisor of the length of all its cycles is equal to 2. So this component is periodic, and the period of this component is 2, okay? Okay, now, I don't know if, I mean, I understand that if you didn't see this before, probably you don't understand very much what I'm saying. And if you know it, I mean, everything is a bit trivial. But let me make these two important remarks. The first remark is that obvious remarks. Each graph has at least one sink component. And the second remark is the following: is there exists a single sink component, all its nodes are globally reachable. No matter where I start, I can eventually reach those nodes. This is also used probably, I mean, I will use it later. Okay, now let's address now the problem of consensus. So when does a linear system reaches consensus? Well, I think it should be clear that the linear system linear system x of k plus 1 equal axk reaches consensus if and only if there exists a vector w such that when I do the limit for k that goes to infinity of ak, I get a matrix that has all the rows identical, and each row is equal to this vector w, okay? So in this case, we can say that matrix A is consensual. It's not a standard term, but I want to use it because I think it's easy to explain things like this. So a consensual matrix A is a matrix that allows us to reach consensus. Now, why this property must hold? Well, it's easy, I think, to understand. This is not a proof, it's just some observation. The limit for k that goes to infinity of xk is equal to the limit of ak times x0. We said it before. So I have to look for if there exists the limit of this matrix. And if the limit of this matrix is this, is a matrix where all the rows are identical, when I multiply this by x0, I get a vector where each component is W transpose x0. So all components are identical. I've reached consensus. I want also to point out something. Look at this condition. It is a sufficient condition for consensus. It's very easy to prove it. I won't prove it. But I can say that a matrix A is consensual if it has a spectrum where its n eigenvalues are, well, it has an eigenvalue lambda equal 1 that is simple. No, I mean, it's the only, it has multiplicity 1. It has right eigenvector, a vector of 1s, and all other eigenvalues are inside the unit circle, okay? It's very easy to understand why this is happening, because if I consider the initial condition and I project it along a basis of eigenvectors, then all the eigenvalues except the first one, lambda 1, are strictly inside the circle.